Hi, I'm Anthony Tran, and this is my final presentation for CS 4632 Modeling and Simulation. My project is an agent-based financial market simulation with competing trading strategies. Over the course of this semester, I built, tested, and validated a simulation that models how autonomous traders interact through a centralized limit order book. Financial markets are complex systems where many different traders, each with their own strategy, interact and collectively determine prices. I wanted to investigate three questions. First, how do different trading strategies perform when they compete in the same market? Second, how does the mix of trader types affect market stability? And third, what emergent behaviors arise when traders make decentralized decisions? To answer these, I built an agent-based simulation from scratch in Python. Here's the architecture of my simulation. There are four core components. The simulation controller orchestrates everything. It manages the configuration, runs the time step loop, and computes performance metrics. The market maintains the current price and best bid and ask. The order book is a heap-based priority queue that matches buy and sell orders using price time priority, and each trader is an autonomous agent with its own strategy, cash, and inventory. I implemented three trading strategies. Random traders act with a fixed probability and placed orders near the midpoint with random noise. Momentum traders look at the recent price trends, and if the price has been going up, they buy. If it's been going down, they sell. And mean reversion traders do the opposite. They compare the current price to a moving average and trade towards the mean. Each step, traders decide whether to participate, generate an order through their strategy, and the order book matches all orders by price time priority. Let me show you the simulation in action. The simulation config data class has over 20 configurable parameters: numbers of traders, strategy fractions, simulation duration, random seed, and strategy specific settings like look back windows and thresholds. When I run it, each time step processes all traders, matches orders in the order book, updates the price, and records metrics. Now let's take a look. The system exports time series CSV files, summary JSON files, and configuration files for each run. This made it straightforward to scale up to hundreds of runs for the analysis phase. In Milestone 3, I ran 12 initial experiments varying three parameters: number of traders, trader composition, and simulation duration. This first chart shows the baseline price evolution. You can see the stochastic price path generated by the order book matching mechanism. This second chart shows how different strategies performed across configurations. Even in these early runs, I could see that momentum traders tended to earn higher returns in balanced markets, but the results varied a lot depending on the configuration. This variability motivated the much larger analysis in Milestone 4. For Milestone 4, I ran 298 total simulations with rigorous statistical methodology, 10 replications per configuration using different random seeds, and 95% confidence intervals on all results. Starting with the number of traders, as you increase from 5 to 120 traders, mean price returns go from negative 2% all the way up to 175%. Volume scales linearly, and importantly, the bid-ask spread narrows from 47 cents down to 20 cents, which matches real-world market microstructure theory that more competition tightens spreads. The momentum fraction shows something really interesting: a non-monotonic effect. Moderate momentum, around 33%, produces the highest returns, but when you push it to 90% momentum, returns actually go negative. This is because when everyone chases the same trend, they create overcrowded trades and rapid reversals. This heat map summarizes all the sensitivity indices. The biggest finding is that the mean reversion fraction has a sensitivity index of negative 8.65 for price return. meaning small changes in stabilizing agents produce large changes in market outcomes. I also tested 5 realistic market scenarios. The normal market has balanced composition. The flash crash scenario has 80% momentum traders simulating a cascade. The illiquid market has only 5 traders. The momentum bubble has 60 traders with 70% momentum over 1,000 steps, and the stable scenario has 80% mean reversion. The results are revealing. The flash crash scenario produces a jump rate 6 times higher than normal. Frequent, large price movements, just like a real momentum cascade. The momentum bubble generates the highest returns, but with huge confidence intervals, reflecting the unpredictability of trend driven markets. This chart shows per strategy returns across scenarios, and the key finding is that no single strategy dominates everywhere. Momentum does great in normal and bubble markets, but struggles in flash crashes. Mean reversion earns modest but positive returns in every single scenario. It actually performs best during the flash crash by trading against the cascade. These price paths visually show how different each scenario looks, from the strong uptrend in momentum bubble to the flat stable market to the crash and recovery pattern in the flash crash. For validation, I used 3 approaches. First, face validation, checking that the simulation produces intuitively correct behavior. More traders should tighten spreads, and they do. Momentum should create trends, and it does. Mean reversion should stabilize prices, and it does. All 5 checks passed. Second, I tested 8 extreme conditions. Boundary cases like 1 trader, 500 traders, 100% of a single strategy, and 10 steps versus 5,000 steps. With 1 trader, 0 trades occur, which is correct since you need at least 2 participants. With 500 traders, volume explodes to over 33,000 trades with near zero volatility, an extremely efficient market. The 5,000 step run shows stable behavior with no numerical overflow, confirming the simulation handles long durations gracefully. Third, I compared outputs to established stylized facts from empirical finance. The simulation matches all 4 tested facts: spread narrowing with liquidity, hurting amplifying volatility and producing excess jumps, zero centered returns, and efficiency scaling with participants. One known limitation is the absence of volatility clustering, the autocorrelation in squared returns seen in real markets, since the model lacks Garch type feedback. To wrap up, here are my 4 key findings. First, trader composition is the dominant driver of market behavior. The mix of strategy types matters more than the total number of traders for determining market stability. Second, moderate diversity produces the most realistic dynamics. Balanced markets behave most like real financial markets, while extreme compositions create degenerate behavior. Third, no single strategy dominates. Each strategy has conditions where it excels and conditions where it struggles, which create a natural strategic ecosystem. And fourth, the simulation successfully reproduces several stylized facts of real financial markets, validating its usefulness as a research tool. For future work, I would add transition comps and order cancellation, implement market maker agents, and calibrate parameters against real historical data. Thank you for watching. The complete code is available on my GitHub repository tagged as Final Submission.